So welcome back. Now we have already discussed about the modeling method of used in the multi-phase flow. We have also discussed about the measurement techniques which we use in multi-phase flow. Now what we are going to cover is the different type of the reactors which is being widely used in the multi-phase flow. So I am going to classify it in the three type. One is the gas liquid system, with which I am going to discuss about the bubble column. Then we will discuss about the gas solid system, in which I am going to discuss first fixed bed, fluidized bed, circulating fluidized bed, and then we will see that if there is any problem or any other type of reactor, generally we are going to discuss only these three in the gas solid. And if needed, if you want, we can discuss some other thing also. You just put a request on the forum and I will try to resolve some of the issues. So now let us start with the gas liquid system, and one of the popular reactor in the gas liquid system is bubble column. Okay. Now there are several gas liquid systems there, which is like a stirred tank reactor is there, air lift reactor is there is a Venturi kind of a scrubber kind of a reactor is there, but most commonly used gas liquid reactor is bubble column. Now what is the bubble column? The bubble column is, there is a pool of liquid is available. This is a column in which a liquid pool is available. So suppose this is completely filled with the liquid, say till this height, pool of liquid is there, and we sparge the gas from the bottom of the column. Now once we know that, once you sparge a gas or once you inject a gas in the pool of the liquid, because of the surface tension property, the gas will be breaked into the small bubbles and it will flow in form of the bubbles. Instead of the continuous, it will flow in form of the bubble, and that's the region that why it is called bubble column. In general, bubble column is being operated as two ways, that liquid is in the batch, gas is in continuous, or both the liquid and gas can be in continuous mode. But generally speaking, the gas superficial velocity is much higher compared to the liquid superficial velocity. That is one of the thumb rule of a bubble column. So what it means that the gas phase is going to be dominating, gas velocity is going to be dominating compared to the liquid velocities. Momentum exchange wise, this may be different, but what we are saying that right now the gas superficial velocity is going to be dominating compared to the liquid superficial velocity. So that is called the bubble column. The L by D ratio for the bubble column, generally they are very taller. L by D ratio varies from 2 to 20 generally, and the superficial velocity of the gas is varies up to 50 centimeter per second. So this is not a very high velocity, but not up to very low velocity also. So industrial scale, this is the way the gas liquid column or bubble column looks like. There is a column in which you sparge the gas from the bottom. Now for better bubble size, better bubble distribution, different type of sparger is being designed through which the bubble is actually injected inside this. The liquid can be injected in the co-current or in the counter current mode, or it can be kept in batch, and the gas will move upward. Liquid will remain this kind of either in batch or in continuous, depending upon that the liquid movement will be there. It will move with the bubble because of several forces which will be acting, like drag, virtual mass forces, which we have already discussed, and which will try to show some of those correlations again, how you can use it in the bubble column to model or to understand the behavior of the bubble column. This is typical this, and most of the gas liquid reactions are being carried out in the bubble column because of the better contact efficiencies. There we have already discussed about, so this becomes a typical example of gas liquid flow in a vertical pipe. We have already discussed the regimes of that, but that regimes while discussing we assume that both are flowing together in co-current manner. Here the liquid can be in batch. Moreover, the regime is going to be the same. The only change is that this gas superficial velocity is going to be dominating. And while discussing the regime in the gas liquid, we have discussed the regime where we have varied the liquid flux, we have varied the gas flux, and we kept that the gas and liquid flux can be also equal. So this is a small portion of it. You will going to have operate at a higher gas velocities compared to the liquid velocities. The major advantage of the bubble column is that as a very simple construction, as I said, that is just a column you have to take. You have to put a distributor or a sparger which can distribute the air inside. The liquid, if it is in the batch, it makes your system further simpler. You don't need any pump. You have to just dump the liquid inside. You pass the gas will react with the liquid. There will be some mass transfer will be taking place between the gas bubble and the liquid. Find the different theories available, penetration theory, surface renewal theory, film theory. I am not going to discuss all those things. Please revise it for the better understanding that how the bubbles do the mass transfer with the fluid. So construction wise it is very simple. There is no moving part inside. You are just supplying the gas through a pipeline which is stationary, whole column is stationary. If moving part is not there, we know that wear and tear losses will be not there, or it will be very low, so your maintenance cost will also be very low. Okay. Then it has the ability to handle the solid. If you want to operate a 3-phase slurry bubble column or 3-phase column, you can easily do that. So you can do it with the catalyst also. If you don't have the catalyst which is in the bulk phase available or say liquid phase available, you can use solid also as a catalyst. It can easily handle that. And the most important, and why it is being widely used for the reaction also, the edge of temperature control. It can control your reaction properly because of the huge volume of the liquid present. So if the reaction is exothermic, there is a liquid available to control, cool down your kind of reaction temperature and maintain a proper reaction condition. So the control of the temperature is edged, is better, and that is the major advantage. And because of this, the bubble column is used for most of the gas liquid system. Bubble column is one of the preferred choice to perform the experiments or perform the reaction. Now what is the disadvantage? The first disadvantage is, as I said, that L by D ratio is going to be very high. You are pulling the whole thing, whole reactor, we are filling with the liquid, so you are going to have a very high pressure drop. And why it is there? Because of the static height of the liquid. So you will have to have that much static height of liquid you have to do. So suppose if the column length is 1 meter, that static pressure will be rho g h, rho will be of water, say g into h. So that much pressure you need, and that will be the pressure drop you are going to see minimum. So that is the disadvantage. You are going to have a high pressure drop due to high static head of the liquid. The gas liquid area decreases if the liquid, if the ratio of height to the diameter exceed 12. So if you are operating at L by D ratio more than 12, then the gas to liquid area is being decreased. So that is the another advantage, and because of this gas liquid area decreases, the bubble start coalescing. So if your height is very high, you are sparging the bubble from the bottom. So suppose this is your column. If the height is very high, you are sparging the bubble from the bottom in form of the kind of air from the bottom in form of the bubble. With height, what will happen? Because of the friction near the wall, the air will try to avoid the wall. So what will happen? The air will try to come at the center of the column. All these bubbles which is being injected throughout the periphery will start trying to come at the center of the column, because the resistance at the center of the column is low. And as we know that fluid follow always a path which is of the lower resistance, the gases will try to move at the center. So if your height of the column is too big, these bubbles will come closer and they will form a bigger bubble. And the moment it will form a bigger bubble, what will happen? The surface area will reduce, and the gas to liquid contacting surface area which is around the bubble will also be reduced. So that is the disadvantage another, that if you go for a very big system, the bubble coalescence becomes a major critical issues, and lot of work has been done to understand that how we can minimize the bubble coalescence. But by and large, this is the column where the maintenance cost is almost zero, operation is very easy, controlling is very easy, and that's why for most of the gas liquid operation, till it is not needed otherwise, bubble column is being used. Now there is different flow regimes occur in the bubble column. The main regime which is being used at the industrial level is bubbly flow. In the bubbly flow, you can see the photograph. This is a typical photograph of the bubbly flow. The small teeny bubbles are formed. So if you zoom it, you see the small teeny bubbles are formed, and generally speaking, there is no coalescence. The individual bubbles moves upward individually, and there is no critical coalescence, not much dominating coalescence take place. The column is generally calm, and the only problem here is that the throughput of the gas is very small. And because we want higher throughput system, we generally operate at a higher gas velocity, and that means you are going to transfer in the churn turbulent flow. In churn turbulent flow is what? There is different turbulent regime is being formed, different structures are formed inside, bubble coalescence is being dominating, and you see the big higher bubble size distribution. The bubble size distribution is really big. It means the phenomenon occur at different length scale. For the smaller bubble, the phenomenon will be different. Bigger bubble, the mass transfer will be different. So the phenomenon or the reaction will be different. So this system will be more dynamic, and the analysis of the system becomes more tough compared to the bubbly column. Overall, the regime wise, if I say that this is the two regime generally we want to operate, but overall regime occurs in the bubble column in the vertical system is pretty much similar to whatever we have discussed for the gas solid system, but the only kind of systems you will get where the liquid volume flux or liquid volumetric flow rate are lower. So if you remember our initial graphs of the flow regimes which we have discussed about the gas liquid, if you just see that the regime available for the lower liquid volumetric flux, only those you will see in the bubble column, other you will not able to see. So you will not see the dispersed regime and all, okay, or you will not see the annular regime or dispersed regime in the bubble column. So what we are going to do, what we are going to see, if I plot the gas velocity versus the column diameter, or the gas velocity versus liquid velocity, because liquid velocity is very low, I am not going to plot it, the regimes is not plotted in terms of the gas velocity to the liquid velocity, the way we do it in the classical gas liquid flow when it was flowing in the vertical pipe or horizontal pipe. Here we define the flow regime with the diameter of the column. Now, why the diameter is a critical function, we will discuss. So, if your gas velocity is very low, we are assuming that liquid velocity is very low, or let's assume the liquid velocity is 0. So, it's a only batch liquid. So, suppose this is the column, liquid is filled in the batch and we are discharging the gas from the bottom of the column. We are passing the gas. Now, this gas velocity is very low for all the diameter of the system, whether the diameter is very small, say this system, or the diameter is very big, say this system. If I take 3 systems, small, intermediate and big system, for any system, if your velocity is very low, what will happen? If you disperse the gases, a teeny bubbles will form and these teeny bubbles will move upward individually. There will be very low coalescence. So, this system will be called homogeneous regime or bubbly flow regime. So, this is called homogeneous bubbly flow regime, or someone is called only homogeneous regime or only bubbly flow regime, where gas velocity is very low. So, individual bubbles will form which will move upward like this. You will see this picture like this. Generally, for the bubbly flow regime, gas volume fraction is less than around 5%. Now, if you increase the gas velocity, what happens for the smaller diameter of the column? If you keep on increasing, say, gas velocity here, the smaller gas column, what will happen? The bubble will start coalescence. Earlier, when the velocity was low, you will see the teeny bubble. Now, because you are increasing the velocity, so the sparging rate will increase, more and more bubble will be pushed inside the column. So, what will happen? The bubble coalescence will start. They will start interacting with each other and they will form the bigger bubble. Once the coalescence start, they will form a bigger bubble. So, say this for bubbles, smaller bubbles will go, they will have the coalescence and they will be replaced by the bigger bubbles. So, they will be replaced by bigger bubble. The bubble size keep on increasing. Now, if you keep on pushing more and more gas for the smaller size system, there will be a condition comes when the size of the bubble will be equal to the diameter of the column, and that regime is called slug flow regime, where the size of the bubble is approximately equal to the size of the column or diameter of the column, and that is called slug flow regime. Now, this is possible only for the smaller diameter system. Generally speaking, for a system having a diameter of 4 inch or say 10 centimeter. Beyond this, it is very difficult to have bubble which is a diameter of more than 10 or 15 centimeter, because bubble will be destabilized and it will break again into the 2 smaller bubble. So, because of that, the stability of the bubble is not there and it will again break into the smaller bubble. So, for higher diameter system, if you keep on increasing the flow rates, you will go to the churn turbulent regime, which will be having a bigger size bubble distribution. There will be some teeny bubble, some bigger bubble which have been coalescence formed, the bigger bubble, then those coalescence bubble will actually break into the 2 smaller bubble. So, we will see all kind of the chaotic dynamics inside. So, we will see the very wide bubble size distribution. Most of the industries which is being operates the bubble column for reaction purpose. Again, I am quoting it, for reaction purpose under the churn turbulent flow regime to achieve higher yield. But the problem is, if you see that whatever I said, that this is the one of the difficult column to analyze, because we have a different multiple bubble size distribution. So, the analysis or understanding of this kind of a column becomes tricky. The modeling part becomes tricky, whatever the modeling part we have discussed. If you remember, if your bubble size is very small, bubble fraction is very low, for homogeneous bubble, even the algebraic slip model can be used, or Euler model can be used. But if you have a churn turbulent regime, algebraic slip model is completely ruled out. You cannot use that. you can use Euler, or to account the bubble size distribution you have to go for the Euler-Lagrangian, or you have to modify the Euler model by using some population balance model in which the drag is being calculated based on the complete population compared to the one for the better prediction. So, your modeling becomes more and more complicated. You need to understanding wise, it is difficult to understand this system. Similarly, for experimental measurement techniques, if you are operating bubbly flow regime, any technique will work because your volume fraction is less than 5%. If your gas holdup will increase, as I said that your volume fraction will be too high discrete phase, the analysis will be difficult and optical based technique cannot be used. Even the intrusive technique cannot be used, and you have to go for RPT or MRI or PEPT kind of a technique to analyze the system. This systems is very typical, very difficult to analyze, and most of the industry operate here. So, what we are going to see that this based on this regime actually, and based on that operation, as I said that the major problem comes in the churn turbulent regime because you have wide bubble size distribution, lot of different bubble type columns is being introduced, where different types of the bubble column is being introduced to come over that bigger bubble size distribution problems. What people have done, people have start putting the internals, vertical internals, horizontal internals, spring, something to reduce the bubble size. So, somehow we can break the bubble size. So, one of the single stage bubble column, simplest column which we have discussed is the single stage, where what you do, you actually enter the gas and liquid. Okay, the gas comes from the bottom, liquid comes from the co-current or counter current manner, and you can pass it. Now, what will happen if you are operating at a higher throughput? As I said that the bubble size will change. You need to break that bubble size to have a better control on the mass transfer and better control on the dynamics of the bed. What people have done, they have put a different sieve trace kind of, which is being used in the say distillation column also. So, what will happen? The idea was, if you do put a different sieve, what will happen? The bubble which will be generated, the moment it will get bigger, the sieves will come and it will again break the bubble into the smaller size. So, that is the way the multiple stage bubble column is being used, but there was a problem in this stage also, that the bubble fraction, the bubble adhere near the surface, the bubble fraction increases, the pressure drop increases, and that's actually complicate the problem physics. Then vertical, instead of the horizontal sieves, the vertical rod is being introduced and multi-channel bubble column is being there, with the idea of the same, that the moment the bubble size will get deeper, bigger, this rod will come in between, it will break the bubble, or the bubble will not able to grow more than this thickness. So, more than this thickness the bubble size cannot grow. So, more than it will not able to grow. So, that is being used, but again this have a major problem with that. You have an internal inside, any hostile medium that internal can damage, and second thing, the bubble will start adhering on the surface. That is the property of the bubble, that if you will see any surface, it will start adhering. So, you will see the more fraction of the bubble near the tubes compared to the other places. The similar thing, this different type of structure is being used, where the mixer is being used, the gas and liquid both is being sparged, with the idea that the liquid will actually break the bubble. So, that is the different kind of bubble column is being operated. The loop kind of a system is being operated, where the bubble and liquid, there is a kind of a two rod is being placed and bubble and liquid work in this loop type. Jet type system is being injected, so that you can minimize the length of this and you can form a small jet, and because of jet, because of the shear of the liquid, the bubble will break into the smaller bubble, and you can see that. The downflow bubble column is being used, where the gas is being injected, and because the top we use the Venturi kind of a scrubber, where the liquid is being flowed at a very high velocity, suck the bubble or gas from the atmosphere and push down. Now, because you are having a very high liquid velocity, the shear of the liquid will break the bubble. The bubble, gas and liquid both are in this case is moving downward. If you will see, they are moving downward. So, the bubble have a natural phenomenon to move upward. Now, you are shearing it against this natural buoyancy. So, what will happen? The coalescence will be minimized. So, downflow bubble column is also being used, three-phase bubble column is also being used, and there are several other column is also being used. People have put vibrating internals inside, so that internals will vibrate, it will break the bubbles. So, all these things has been generated to minimize the bubble size distribution, to keep the bubble size distribution uniform, because what we want from this reaction is better mass transfer. And if you want to have better reaction, the mass transfer limitation should not be there. If your bubble size increases, surface area reduces, mass transfer reduces. So, that is the typical catch here, which we need to understand, and that is why there is lot of effort goes on in the literature, if you will see, to design a new type of bubble column where the size of the bubble can be maintained. Now, what is the typical issue? If we go for design of the bubble column, I will solve some of the equation, but I am not going in detail of this because these are individual topic of research which require great time. I am just giving you a glimpse of everything here. So bubble column design, what is the typical issue? The first thing is that gas holdup, that how much gas holdup is there, and that gas holdup is directly related to the velocity, that how much velocity you are using. So if you are having a higher throughput, higher holdup will be there. If you are using lower gas velocity or operating at a lower throughput, lower holdup will be there. There are several correlation is available. Again, I am not going to favor any correlations. There are several correlation is available. People can have their own choices for the correlation, but most of these correlations are developed, and those correlations is a function of superficial velocity of the gases, liquid density, surface tension, and liquid viscosity. So these are the correlation being used, and the bubble holdup is generally the function of these 4 parameters. Now these powers can be different. There is some constant value can be there to have that correlation. Now what is we want to measure? You want to measure KLA. Now this is the major problem in the bubble column, that you want to maximize not the only surface area, you want to maximize KLA. Now the K is the mass transfer coefficient, that depends on the bubble size also. A also depends on the bubble size. Now what will happen? The KLA value will increase if I increase the surface area, but if I make a bubble very teeny, say micro size bubble, okay, what will happen? The K value will drastically go down because the mass transfer through the bubble will not be there. This is small particle of nano size bubble or micro bubbles will behave like a bullet. They will not do any transfer with anything. So what will happen? The K value will go down, and again increasing the surface area is not going to help you. So what we see, we want to maximize the KLA value. We don't want to only maximize A. That is the wrong notion people have, or many people think that you just keep on reducing the bubble size, your mass transfer will increase. That is not going to happen. You have to have KLA, you have to think about the KLA. The KLA, actually the K value is reduces with reducing the diameter of the bubble. A value increases with reducing the diameter of the bubble. So you have to have an optimal values. Now this KLA again is going to depend, because this depend on the size of the bubble. It is definitely going to depend what is the gas velocity, what is the density, what is the surface tension, viscosity of the gases, viscosity of the medium, the diameter of the column and diameter of the bubble, and what is the buoyancy forces which is acting on it. So delta rho, these all are depending on that. Then axial dispersion, it occurs both in the liquid and the gas phase, and you should understand that what will be the axial dispersion of the gas and what is the axial dispersion of the liquid. Then another important parameter is the mixing time. How much time liquid is in the mixing, gas will go up, liquid will move upward with the gas bubbles, and then because the gas will erupt outside on the top of the liquid layer while the liquid will come down. So you will see a circulation profile. Okay, so suppose if I am sparging the gas here, what will happen? The bubble will form. Bubble will say move at the center of the column. As I said that even you sparse at the bottom, because of the higher resistance near the wall, the bubble will try to come at the center of the column. So what will happen? Liquid will move with the bubbles because of the drag and some virtual mass forces which will be acting here. So bubble will erupt outside, it will go outside on the top layer of the liquid, but liquid cannot go outside, so it will come back. So you will have a mixing. So it is important to find that what time it will take to achieve the complete mixing of the liquid. Again, lot of correlations are available that the mixing time for the mixing time calculations. Then volumetric flow rates and residence time of the bubble is also important, that what is the residence time of the bubble inside, what is the flow rate you are operating, and then the another most important thing is which regime you are operating, whether you are homogeneous, whether you are heterogeneous, or whether you are slug. Generally most of the industry is being operated at heterogeneous regime. So these are the design parameter which one require to understand the bubble. The another design parameter which is required to understand or to have the knowledge is about the physical properties. So what is the liquid and the gas we are using, what is the property of it, and this physical property is very important to determine the coalescence and the mass transfer. So suppose if you are using a surfactant, some having a surfactant property, you can reduce the coalescence. If someone having a property which is kind of some kind of electrolyte or something is being there which is kind of favoring the bubble coalescence, you will have a bubble coalescence. The bubble coalescence will increase. Similarly, the mass transfer is going to get affected based on the liquid physical properties. So you should have the liquid property, the physical properties of the liquid should also be known. The good correlations are available for the air water system, but these are limited for a particular range. So these correlations are available only for air water system. For the different fluid, these are limited, we are not very sure whether the correlations will be used or not, and this range is also limited for that. The correlation may not be available for large scale system or the system with vessel geometry other than cylindrical. So most of the work has been done on cylindrical column without having any internals. If you use the internals, if you use for the large geometry, if you use for a column which is not cylindrical in nature, particularly, these correlations cannot be used, or maybe the validity of these correlations, whatever has been discussed, will be questionable. And then the experimental correlation may not be accurately reflect the phenomenon which is occurring inside, particularly when the regime transition take place. So most of the correlation developed in the bubble column is empirical based correlation. There are certain correlation which is phenomenological model is also being developed, but those models or those equations is being developed only for a particular flow regime. They are not going to work if you are not operating in that regime, or the regime change is taking place, or the transition is taking place in between. So these things one need to be careful before analyzing the system or before using those correlation for the design of the bubble column. So measure what is the parameter which is affecting the bubble column performance, or what are the important parameter which is in the bubble column is there. There is mainly 3 parameter. One is bubble size, one is the bubble shape, one is the bubble rise velocity. So these are the 3 typical parameter, that what is the size of the bubble you are forming, what is the distribution in that size, what is the shape of the bubble, whether it's a spherical bubble, elliptical bubble, lot of wobbling bubbles, okay, spherical cap bubbles. There are different type of the bubbles available. What are those kind of bubbles you are operating, and the correlation I am talking about is depend on the bubble size, depends on the bubble type, depend on the bubble velocities, that what is the bubble velocities is there. So I am not going to discuss about all those correlations. They are widely available in the literature. You can search for the correlation, you can use the correlation of your choice, but I am going to discuss the basics which we have done in our multi-phase course, that suppose if I have to find in any bubble column that what will be my bubble size distribution, how I can get, or what will be my bubble size, how I can get from my basic physics which we have learned in this course. Okay, we will not able to get the distribution. Ideally you can get the distribution also, but that is not the part of this syllabus. So suppose if I have to find the bubble size. Now the bubble size, it will depends on what. So suppose there is a liquid which is filled here, and you are sparging gas from the bottom, and this gas will form a bubble. So what will happen, how it will form the bubble? Initially the bubble will generate on the surface. Initially it will generate on the surface, okay, say make it more smaller. Initially it will generate on the surface, and how it will generate? First, once you pass the bubble, a small amount of the bubble, a small air will be there, and that air will not go out because it needs certain buoyancy before it lift up, before it detach from the surface. So what will happen? It will first grow around the surface. Now once it will grow around the surface, there will be surface tension forces which will be playing a role. Then buoyancy will be playing a role, that when it will be detaching. The momentum flux, the gas momentum flux will be playing a role, because you are putting the continuous gas inside, so that will be increasing the momentum flux of the gas. That will be playing a role, and that will determine that when it will detach from the surface. Inertial forces will be playing a role, which will be actually determine that it will not detach from the surface. We will discuss about all those forces, and then once it lift, drag force play a role. So the forces which are important to determine the bubble size is buoyancy, okay, the buoyancy force, the gas momentum flux, the gas momentum flux, and that gas momentum flux favor the detachment. So this is the force which will favoring the detachment, that how it will detach. Then you are going to have surface tension force, then you are going to have drag which will be acting here, and then the inertial force. So these are the forces which are going to determine the size of the bubble. Now how they are going to determine the size of the bubble? We are going to do the force balance. So now first see that how to write the buoyancy. Now the buoyancy acting on this will be definitely because of the density difference between the gas and the liquid, also because of the pressure difference. So there will be a gas pressure inside the bubble, there will be a liquid pressure outside of the bubble, and that pressure difference will also add into the buoyancy, which will cause the bubble liftment, which will cause the bubble to move upward. So the buoyancy force will be little bit modified with the regular buoyancy, and that will be pi d cube upon 6 into rho of liquid minus rho of gas into G. So that will be the buoyancy forces, the volume of the bubble, rho L minus rho G into D, okay, where D is the diameter of the bubble. Rho L is the density of this liquid, rho G is the density of the gas, and G is the gravitational forces. Plus you will see that the pressure force. Now the pressure force will be, because this pressure is force per unit area, I am going to multiply with the diameter or kind of area. Now which area we are going to multiply? Suppose if I am passing there is suppose a C plate, there is small holes made on the bottom plate. So the diameter of this hole say is the D naught. Then what will happen? The pressure will be, this bubble will be growing along this diameter, say it will be growing along this diameter in this way before detaching. So the area, the pressure will be acting on the gas phase pressure and the liquid phase pressure on this area. So this will be pi by 4 into D naught square. So I am going to take D naught, which is the diameter of the orifice, the hole which is being placed. I will write all the notation here. Then it will be Pg minus PL. So this is the total buoyancy force which is going to be act. The Pg and PL is the pressure difference inside and outside of the bubble. Inside the bubble the pressure is Pg, PL is pressure outside of bubble. So this is the pressure difference inside and outside of the bubble. So this is pressure difference inside and outside of bubble. This is the buoyancy force. Anyway, so this will be the forces which will be acting on this. D naught is the orifice diameter, and D is the bubble diameter. So this will be the buoyancy force which will be acting on this. Now there will be some momentum force acting on this, momentum flux of the gas which will be acting on this, and if I convert that momentum force, the momentum of the gas, so F mb, where I am saying that momentum force of the bubble or the gas which will be acting on the bubble, which will be maximizing or kind of helping in the detachment from the surface, because gas you are completely injecting, that momentum flux is what? That is going to be rho into the velocity u naught square. So u naught into u naught. Now u naught is the velocity of orifice velocity. So u naught will be equal to what? It will be q divided by the area of the orifice. Okay, so it will be q divided by pi by 4 d naught square. Now if suppose you have a multiple holes, then what will happen? You have to multiply n also, so that will get the individual velocity, that how many suppose number of holes, so that you are getting a one hole area, say 100 number of holes is there, you have to multiply it with the n, so you will get the velocity from the individual holes, because this q will be distributed. Again assumption is q is uniformly distributed across all the holes. So that will be rho, say I am simplifying the case, I am not complicating it much, so making it one hole orifice suppose. So this will be pi by 4 d naught square again. So this is the flux, and if you want to convert from the flux to force, you have to multiply with the area again. So pi by 4 d naught square into rho u square. So that will be the momentum flux force. Now surface tension force, this is the momentum flux, gas term flux force. This is buoyancy force. This is the momentum force, this is surface tension force. Surface tension force is what? It is going to be pi d naught into sigma. That will be the surface tension force, where sigma is the surface tension. So that is the surface tension force which will be acting on that. Then there will be a drag force which will be acting, Fd. Fd, as we have discussed, it is going to be the area CD into rho into u square. Now u will be equal to what? U of bubble square divided by 2, because drag will act once it will be detached from the surface. So now it will be not the orifice velocity, it will be the bubble velocity at which the bubble is moving, into area, and area will be the bubble area, pi by 4 d square. So this is bubble velocity or bubble rise velocity, Ct, and d is the diameter of the bubble. Okay, and this is CD, not this, and rho is the rho of gas, density of the gas phase. So that will be the drag force, this will be the drag which will be acting here. Now what you are going to see is the inertial force. The inertial force or the force which is being acted on the bubble acceleration point of the detachment, and this force is due to the continuous increase of the bubble buoyancy. So, what will happen? The bubble buoyancy will increase, it will try to detach from this place. Now, because it will try to detach from this place, what will happen? That the liquid which will try to come and replace that bubble. So, that is the place where the inertial force will be acting, and that inertial force Fi, which actually reduces the bubble detachment, is going to be rho of G into V plus rho of L into V of L into UB, which is the bubble rise velocity, into time, or you can say the TD, which is the detachment time. So, this much is the inertial force will be acting here. This inertial force is actually what is going to be the function of the velocity, that volume of the bubble. This V is the volume of the bubble, and this VL is the volume of the liquid. Okay, and B is bubble rise velocity, and this is called inertial force. So, what happened? The bubble accelerate up to the point of detachment, and why it is kind of this accelerate? Because the buoyancies keep on increasing. So, because of that the bubble kind of accelerate, and that acceleration force is being added, which is called the inertial force, and this acceleration force actually try to minimize the bubble detachment from there. So, if you see this term rho into VL is what? Is the amount of the liquid, this is rho L into VL, which is being moved along with the bubble. So, bubble once it will move, there will be certain mass of the bubble which will be moving, okay, and with that mass of the bubble, if you see, this is the rho G, which is density of the bubble multiplied by the volume of the bubble, it means certain mass of the gas which is moving. Now, once the certain mass of the gas will be moved, it will take certain liquid along it, and that is called virtual mass force or added force, which we have already discussed, which is very high in the bubble column. So, that will be moved, and then you are seeing that at what rate that mass is being transferred. So, that way you are calculating that what is the acceleration through which bubble is moving. So, what is the bubble acceleration in terms of this? And that bubble acceleration is nothing but the inertial force. So, that is the way we are being kind of calculating the inertial force. It is the total amount of the mass, gas plus liquid, bubble is taking away. So, that is the inertial force. Now, these are the forces which are important to determine the bubble size, because the bubble, what is happening, growing on the surface, buoyancies keep on increasing, the drag force will act once it will be lifted up, the buoyancy is increasing, gas momentum flux is increasing, inertial force is kind of trying to stop the detachment. Completely together it will determine that what will be the size of the bubble. Obviously, surface tension is also playing a role. In a more simpler assumption, what we can say that I am neglecting all these forces, and the bubble size will be mainly governed with the buoyancy force and the surface tension force. Okay, so that is the kind of simplest assumption you can have, that the buoyancy and the surface tension together will determine the bubble size. All the other forces are negligible, and you can easily assume that the pressure gradient within the bubble and outside of the bubble is same. It means the internal recirculation of the bubble you are now neglecting. So, if you neglect that, the pressure gradient will be the same across one bubble. So, the buoyancy force which we have developed here, this term will go out. This term will be 0 if you assume that uniform pressure gradient along the bubble. So, what will happen? You will see that pi by 6 d cube into rho L minus rho G into G, that will be equal to pi sigma into your d naught. D naught is the orifice diameter. So, what you can do? You can find the size of the bubble, d, which is the size of the bubble, will be equal to 6 sigma d naught upon rho L minus rho G into G. So, that will be your size of the bubble, and this will be equal to 1 by 3 power. So, for the simplest case when buoyancy and surface tension is important, Okay. You can find that what will be my size of the bubble. So, if you tell me what is the fluid you are taking, what is the surface you are taking, the surface tension will be defined. Orifice size, if you tell me the gas and liquid, you will get this equation. Many books, if you see that, they will just give you the rho L, assuming that rho L is very greater than rho G. So, suppose like in air water system, density of the air is 1000, density of water is 1.2. If you remove from 1000 to 1.2, you are going to be approximately same value. So, many of the book actually say it rho L into G, but overall this is the basic at which the bubble size is being calculated along one orifice. Now, we are not thinking about anything bubble coalescence, because bubble coalescence happen once the bubble moves upward. Now, if you don't want this, if you want to have really great equation or good equation for the bubble size, what you have to do, you have to take all the forces into the account. Now, what will be the forces? The forces which is helping in detachment, forces which is helping or kind of obstructing the detachment, that two will be equal, and then the force balance will be there, then only the bubble will detach. So, that will be the forces will be added Fb buoyancy force plus F of momentum of the gas mg, that will be equal to F of surface tension plus F of drag plus F of inertia. So, this is buoyancy, this is momentum flux of gas, this is surface tension force, this is drag, and this is inertial force. So, you can do this force balance, and from this force balance you can find it out the bubble diameter. Definitely the equation will be more typical, it will not be that easy. What I am going to do, I am going to write the final equation, you can do it, and if there is any problem please let me know, I can share the solution, but it is just the transformation, and if you do that you will get that d cube will be equal to 6 d naught sigma upon rho L minus rho G into G. This is the first term which is coming because of Fs. Okay. So, if you will take this term will come, then it will be multiplied by 1 minus Weber number upon 4 plus it will be 881 into mu, okay, of liquid, which is viscosity of the liquid, Q of gas, volumetric flow rate of gas, into pi, it will be rho L minus rho G into Gd plus 135 upon 4 pi square plus 27 rho G upon pi square rho L multiply by rho of L into Qg square upon rho L minus rho G into Gd square. So, this will be the overall thing you will get it in form of the Weber number if you solve all this. This is just what I have done, I have just changed the velocity in terms of the flow rate, so that you go out of this orifice diameter, you just get the terms which is kind of globally available. So, all the other terms I have kind of changed, transformed into the other part. So, you will get this equation where We is the Weber number, We is equal to Weber number, which is presenting the ratio of inertial force to the surface tension force, and important in determining the size of the bubble. So, it is the ratio of inertial force to the surface tension force, and if you solve this, the inertial force, it will be rho G into u square or u naught square, because you are going with the orifice velocity, into d naught upon sigma. So, that is the Weber number, inertial force to the surface tension force. So, that is the way Weber number is being defined, and you can find it out the equation for the bubble diameter. Now, several authors had done lot of simplification, some forces has been neglected and different equation for the bubble diameter is given, but this is the basics. And we are not discussing again about the bubble size distribution, we are just saying that if you inject in the column, you can calculate that what will be the bubble size, and this bubble size you can use to in your simulation to calculate the drag. Now, other parameter about the bubble shape and bubble velocity we will discuss in the next class. Thank you.